Hello, everyone. I was muted. Sorry. And I'm sorry I cannot be there. You can hear me now, right? Yes. Okay, very good. So this is the first time I do this format of presentation, presenting other people's papers and critiquing it at the same time. So I don't really know what's the right way to do it. I think Alan gave a very good example, but that's too late for me to learn. Um, anyway, so Eric very kindly shared his slides with me. So this,
No, it's very.
Okay, we're not listening to you very well, Xiaoxia.
you cannot hear me very well.
Now it's better.
She could speak up perhaps.
Yeah,
Speak up a
we're
bit.
not. Yeah.
Let me see. So the microphone I'm using usually works. Let me change to a different one and see whether that works.
Okay. This is actually better.
Is this better now? No.
No, that's worse.
Yeah, that's worse.
That's worse. Yeah, worse.
Is it better now? I just hold the microphone to my face then.
Yes.
I think
Yeah,
that works
better.
better. Okay, so let me just do this the whole time. Okay, so I want to thank Eric for sharing his slides, and so this set of slides will be made based on what Eric made. I will add my comments as well as I go along. So this paper is a nice paper that investigate doing bootstrap for model selection. So to begin, let me explain what the model selection is. Okay. So the setting is that you're selecting between multiple models, and selecting between multiple models is obviously a very important thing that people do in empirical work. And so one motivating example, which is also the empirical application, is to select between two or less regressions with non-nested sets of regressors. For example, model 1 is regressing y on x1 and some control variables, and model 2 is regressing y on x2 and some control variables. And you're trying to decide which model is better according to some criteria. In this case, both model could be misspecified in the sense that the true model may be nonlinear, or if you're assuming normal error, as this paper does, maybe the true error is not normal. And the two models you are trying to select among are not nested to each other. So the nested testing procedures do not work here. So a popular approach to this is pioneered by Kwang Zhang's 1989 paper, and that paper is extended by a lot of people. So the Kwang Zhang's original paper has a Google citation of over 7,000, so that probably indicates that a lot of people use this paper, and a lot of people work on extensions of this method. And this lists some recent applications in different areas of empirical economics. So what's model selection test? So model selection test is to select a model by doing a hypothesis test, right? So it's going to be able to tell you which model is better, but not only that, it's going to be able to tell you which model is better in a statistically significant way. So it properly accounts for sample noise. So that's what model selection test tries to do. What this paper tries to do, this paper tries to address two challenges, as Eric writes in his paper and in his slides. But I'm going to talk about, discuss the second challenge. So the first challenge is to design a robust test that will have good size or good type 1 error property, regardless of where the data is generated from. So that is motivated by the fact that the classical bond test is not robust to that. It's sensitive to the data generating process, and that can lead to false rejections depending on where the data is generated from. And this problem was pointed out in these previous papers. And the challenge too is to ensure that the test is not conservative, as the paper says. So a conservative test rejects the null less often than it should. So therefore, sometimes it results in no model being selected in the data. So I have some discussion about this challenge. So one is that I think the paper tries to make this point that it's hard to make the test not conservative, and therefore, and based on the evidence that, based on the claim that model selection tests will not reject the null when the null is false, in practice. But so to make this point stronger, I would think it would be better to give some evidence for papers that use the bond test but fail to reject the null hypothesis. Fail to reject the null hypothesis here means that you're not able to select between the two models. You're not going to be able to make conclude which model is better. So in the paper, I don't see such evidence. So such evidence would be useful, I think, if you want to make this point. And another thing is, it's really about conservativeness, what conservativeness means. So conservativeness basically means the maximum type 1 error probability, so the rejection probability when the null should not be rejected, is less than alpha, not equal to alpha. So that is what conservativeness means in classical textbooks. But I think what the paper tries to, the point that this paper tries to make is that the proposed test has better power. So power is about what happens under the alternative. It's when the null hypothesis is not true. It's when one model is better than the other, is the test selecting that model. So that's what power is about. So that doesn't have a direct connection with conservativeness. So I would suggest that you could make this point better by directly saying that your test has better power. So it's a challenge to design tests with good power. That would be my suggestion. So okay, so what the paper is about, as I hinted, is it proposed a new model selection test that use Bootstrap. It's gonna be robust, meaning that it's going to have type 1 error controlled very nicely, regardless of the data generating process. And this paper also claims that the test is not conservative, but this is not really proved. And so I would suggest making the second goal as, the test has better power, which is demonstrated in a Monte Carlo simulation. So that is a property that is supported by Monte Carlo evidence. This paper also derives asymptotic refinement of the bootstrap, because the test is based on bootstrap, and as we know, in some situations, bootstrap can achieve refinement. But there may be a misunderstanding of the refinement here. So bootstrap refinement means the probability of rejection under the null hypothesis by bootstrap is closer to the nominal size, say 5%, than the normal based test. So it's closer to 5% than the normal based test, but it does not imply that the bootstrap based test has a rejection rate that is bigger or smaller than the normal based test. So that is not what the bootstrap refinement says. And also, because alpha is usually just 5%, right? So, or 1%, that's a small number. And bootstrap refinement usually is in a small scale. So the difference between the bootstrap critical value and the normal critical value will be so small that usually it doesn't have a lot of impact on power. Power is what happens under the alternative, where the rejection rate is a lot higher than 5%. Uh, so, so it is true that the Monte Carlo simulation in this paper shows that the new test has better power, but using asymptotic refinement as a theoretical explanation for that might be problematic. So I will talk a little bit more later as well. Anyway, so let's um, so this is a brief overview of the literature. These other paper also propose uniformly valid tests which have good type 1 error probability. And this new test shows better power property in Monte Carlo simulations. And this new test is easy to implement, even though it relies on Bootstrap, but coding it up, it should be quite easy. So I think this paper can emphasize this point more. Um, so there are other papers that deal with likelihood ratio testing and their non-nested models, but these are not based on Bootstrap. So this is the first test that studies Bootstrap in the model selection testing context. So this paper also did an empirical application. I am not an expert on ACA, so but it appears to me that this paper considers two non-nested models that estimate the enrollment effect based on two policy interventions in the ACA. One is a double quality bonus payment, and the other is the reduction of benchmark, a change of benchmark calculation. And so I believe the paper compares two non-nested regressions, one using the double quality bonus payment as a regressor and some control variables, and the other using the benchmark calculation as a regressor. Both assuming normal error, so the measure of fit is log likelihood, which is equivalent to regression mean squared error. So there is an interpretation for that in the paper, but I have some trouble justifying using the model selection test in this context, even though as much as I like model selection tests, because this seems to be a causal inference framework. And also these two policy interventions may have interactive effect. So yeah, so that's my comment about empirical application. Going into more details, so this is what the Vaughn test is really about. So take these two circles. One circle is one parametric model about the data, and the other circle is the other parametric model about the data. So one model is F, the other model is G. And the data itself comes from a distribution that may or may not be in either of the models. So both models could be misspecified. So in this picture, what's drawn, P0 is the dot at the bottom, which is not in either model. Okay, but they are their closest point to the true value, so that the two dots in on the boundary of the two circles are the pseudo-true densities of the two models. So theta tilde and beta tilde are the pseudo-true values of the parameter. So the model selection test is trying to test whether the distance between the dot at the bottom to each of the dot in the models, whether these two distances are equal or not. So the null hypothesis is that they are equal, they're equally good, and then you can have directional or one-sided alternatives as well. So under this first alternative, the F model is better. Under the second alternative, the G model is better. Okay, when the null hypothesis is rejected, you can see which alternative hypothesis may be true. All right, so what is the test? The test is based on log likelihood ratio. So it's the log likelihood of the F model minus log likelihood of the G model. So written together is the sample average of the logarithm of the ratio of the two density functions. And the parameter values that you plug in here are the maximum likelihood estimators for each model. To make the notation more concise, we denote the log density ratio by lambda I. So the classical Wong test statistic is the studentized log likelihood ratio. So you're trying to basically you're trying to estimate, you're trying to test whether the limit of LRN is 0 or not. And LRN hat is an estimator for that limit. So therefore, it's kind of like a t-test problem. So you take the LRN hat uh, in the numerator and then divide it by the standard error for that estimator, so which is the sample variance of the lambda I variable. So this is the classic wrong test statistic, but then that's only the test statistic. What critical value should you be using? That should depend on the distribution of the test statistic under the null hypothesis. Supposedly, it should be the 1 minus alpha quantile of that distribution, so that the type 1 error rate will be controlled at alpha. But then what is the distribution of the test statistic under the null hypothesis? This is um, what this is the picture that Eric wants to show in his slides. Um, and he was saying that these three cases stands for non-nested models, almost nested models, and nested models. But I think these terminologies may be not standard. So I will explain that in this with this slight modification. So these three cases, remember the two circles stands for the two models. And as you can see in all three cases, they have intersection, right? Non-empty intersections. So they are overlapping non-nested models. And they're not nested to each other, meaning that they're not subsets of each other. So in all three cases, the models are overlapping non-nested. The model relationship is the same. But where the true distribution is different. So the true distribution, you don't know that, right? So you don't know the true distribution when you're doing this testing. It could really be anywhere on this space. If we impose the null hypothesis, then this true distribution should be equally distant from these two circles. But even after we impose the null hypothesis, there are still three possibilities. One is depicted in the first picture, where the true distribution is far from both models, right? So truth is far from both models. In that case, the denominator of the Wong test statistic has a limit that is positive. So that omega square is the variance of the log density ratio that is positive. In that case, the null distribution of Tn, right, distribution of Tn under the null hypothesis is close to standard normal. But in the other two cases, when the true value is close to both models, or when the true model is inside both models, then the distribution of the test statistic under the null hypothesis is not close to standard normal. It's in fact very non-standard. So therefore, it is a challenge to come up with the right critical value for this test, and therefore to come up with a valid test. So, right, the challenge is omega squared. The variance of the log density ratio is not known. And it is therefore non-trivial to achieve uniform size control, which means that uniform size control means we want the maximum possible rejection probability when the null should not be rejected is less than or equal to alpha. That is a basic requirement for hypothesis tests in the Neyman Pearson framework. So that is not easy to achieve. There are non-bootstrap solutions in the literature given by these two papers. And this paper, Eric's paper, proposed a bootstrap-based test and show that it achieves uniform asymptotic size control as well. So maybe a little bit of what's uniform asymptotic size control. As I said, so uniform size control means the maximum rejection probability of the null when the null should not be rejected is alpha, right? So, but you cannot achieve that usually because you don't know the finite sample exact distribution of the test statistic. All you can do is to achieve asymptotic uniform size control. So that's the uniform asymptotic size control. To formalize it, we consider a family of data distributions, P. So that is a family of data distributions. And the sum of the distributions, the variance of the log density ratio is 0. And some other distributions is positive. And let the distribution of a test statistic be denoted JNTP, right? So it depends on the data distribution, right? Because the test statistic depends on the data. And the uniform asymptotic size control would be of this test, of a test that use Tn as the test statistic and CV and alpha as the critical value, right? If you do this test, okay, that's if you reject the null when Tn absolute value is bigger than that critical value, then what does uniform asymptotic size control mean? What that means is when the null holds, you want the probability of rejection. That's probability that the test rejects to be less than or equal to alpha. Okay. Um, so now let's get to the proposed test. So Eric proposed to use this non-degenerate test statistic. It is a little different from the Vaughn test, the classical Vaughn test, right? So the Vaughn test has LRN, the log likelihood ratio on top, and the omega hat at the bottom. And so Eric modifies this statistic by adding a bias correction term on the numerator. That bias correction term makes sure that the test does not bias against small models, doesn't always select a large model with lots of parameters. So that ensures parsimonious models can have a chance to be selected. So and so that is nice. Um, and at the bottom in the denominator, Eric adds a tuning parameter. So 1 over square root n times bn, where bn goes to infinity and bn goes to infinity slower than root n. So that tuning parameter is going to prevent the denominator from being too small. And Eric is going to bootstrap this test statistic to get critical value. So let's see what the asymptotic behavior of this modified non-degenerate test statistic is. So this non-degenerate test statistic is going to be close to standard normal when the variance of the log density ratio is positive. That's when the true data distribution is very far from both models. Then this test statistic is asymptotically standard normal under the null hypothesis. And in other cases, when the true distribution is close to the two models or in both models, then T hat ND, this non-degenerate test statistic, will be close to 0. Now, what's the bootstrap procedure? The bootstrap procedure will take a bootstrap sample, just your usual non-parametric bootstrap sample, and construct the bootstrap log likelihood ratio statistic by plugging in the bootstrap sample. So this should be xi star as well. Sorry, I forgot to add that. So it's xi star as well. So this is the log density ratio evaluated at the bootstrap sample. When you are doing bootstrap testing, you always want to recenter the bootstrap estimator by the original sample estimator, which is the LRN hat computed using the original sample. The reason that you want to do that is to make sure that the bootstrap critical value you get does not blow up even when the data doesn't satisfy the null hypothesis. So you want the critical value to be a bounded thing, otherwise your test will have low power. I assume that this is done in the paper, but it's not clearly stated. And then so you get this LR n hat star, and then you get the bootstrap version of the V and the bootstrap version of the omega, the variance estimator, and then just form the bootstrap version of the non-degenerate test statistic. And then suppose this is the 100A conditional percentile, right, of the bootstrap statistic, right? So this Jn inverse A, Pn hat stands for the empirical distribution of the data. And that stands so that percentile you can calculate by simulating the bootstrap statistic many times. And I think this is what the paper does. So you reject the null hypothesis and select the model 1. If the test statistic, non-degenerate test statistic, is bigger than the 1 minus alpha over 2 quantile, and you reject H naught and select model 2 if that is less than the alpha over 2 quantile. So if the test statistic is either too small or too large, you reject the null hypothesis. Otherwise, you don't, and therefore make no model selection at all.
Sorry to interrupt.
Yeah.
But you have about a 5-minute warning. Apologies.
Okay, I'm sorry. Yeah, thank you. So, all right, so that is what the bootstrap is about. And so this is the rough idea of why the bootstrap might be working, might have the validity that you want. So this is the same picture as before. The first picture is when the true model is very far from both, the true distribution is far from both models. Then in that case, both the test statistic and the bootstrap statistic are close to normal. Therefore, the bootstrap critical value is close to the right critical value to use. And in the other cases, both test statistic and the bootstrap statistic converge to 0. Both of them are close to 0. So it looks like the bootstrap works fine because it always has the same limiting behavior as the test statistic. However, this is quite some distance away from a proof. The main issue is that 0 is not a continuous distribution. When a test statistic converges to 0, you cannot base a test on that 0 distribution. When they both converge in distribution to 0, you cannot conclude that percentile of the bootstrap is the right critical value to use. So the paper, I tried to check the proof of the paper, but it doesn't seem like the paper is the theorem is fully proved. I have a rough suggestion for how to make the theorem fully proved. You may like it or not. I'll just leave it here. All right, so this is the theorem that the paper tries to prove, saying that the rejection probability under the null hypothesis is bounded by alpha, but it's not fully proved. So the bootstrap refinement, as I explained, no refinement result says that the bootstrap p-value should be smaller. So bootstrap refinement really does not have a direct impact on power. All right. So this is a simulation result. It does show that the bootstrap test proposed has better size, closer to 5%. So both are higher than 5%, but the bootstrap test is closer to 5%, and it also has a higher power as well than the existing test. That's nice. I would suggest to do a sensitivity analysis to the tuning parameter Bn, and also be more careful about how you explain about the higher power shown in the Monte Carlo evidence. All right, so this is the empirical application. I really am not an expert, so I didn't show much of it. So what the conclusion is that the model selection test does not draw a conclusion of which model is better. So I will not comment on that because I don't know it, the context. So this is just comment on some terminology that Eric uses. I think he can just look at that himself. So anyways, in conclusion, this paper is the first paper in the literature that investigate how bootstrap works in the model selection test context. And it can be shown to achieve uniform asymptotic size control And in Monte Carlo simulations, it demonstrates better power. So the empirical application sounds interesting as well. So to sum up my comments, I would suggest to be more careful about the power claim. It's probably not due to the bootstrap refinement. There are a lot of differences between this test and the previous literatures, not only bootstrap or non-bootstrap. So just be more careful about that. And also, there is an easy way to complete your proof. So you can try that if you haven't already completed your proof. In any case, keep up the good work. I really do enjoy it, and I enjoyed reading the paper. Thank you.
Thank you.
Cool. I think I have some slides on here.
Okay, yeah, just don't close the Zoom, just close the slides, stop sharing.
Oh,
yeah.
Where's,
I just go to Aaron's email.
I think Aaron needs to disable.
okay.
Maybe Xiaoxia?
Yeah, Xiaoxia, can you stop sharing for a moment?
Oh, I just
Just the slides, yeah.
where my slides are.
I think try maybe the desktop.
Oh.
Aaron, I know she had this all organized. Is it open maybe?
No, but I found them.
Okay.
Cool. Let's do this. Okay, cool. Yeah, well, so, yeah, all right. So, first I want to thank everyone for having me here at the school. Xiaoxia, thank you so much for reading the paper so carefully. Like, I'm super appreciative. Like, that's cool. Yeah. I made some slides ahead of time.
She can't get
it. So you just leave it there,
don't. You can leave it there, just talking to the mic so she can hear you.
Got it. Yeah.
There you go.
Yeah. Cool. Yeah. So Xiaoxia, in case you didn't hear, thanks for reading the paper so carefully. Very appreciative. Then right. I made slides with some of the FAQs I've gotten in the past. Anyway.
Eric, can you share your screen?
Oh. Share screen.
If not, I can probably make things worse trying to. I'm grabbing you. You grab me.
Yeah. Let's do that. Share. And then do that. Okay.
Hey, all right.
Hey, let's go. Cool. Yeah. So I made some slides. Yeah. They're probably not going to address all the comments. But like they're going to address some. And yeah. Also, before I jump into things, just a disclaimer. I work for the government. These are my views, not the government's views. Yeah. There's like a process like for being able to say things officially on the government's behalf and do that. These are my views. Okay. Cool. So right. So I think Xiaoxia, like you had kind of 3 critiques of the paper. I'm gonna really touch on comments related to one of the 3. The first is related to kind of misrepresenting my results about an asymptotic refinement as something related to like some Monte Carlo results about better power. I have thoughts, but like let's discuss the offline, and I think that's a pretty valid comment, and I think pushing me to like, maybe have a theoretical reason why I'm getting nice power properties is a totally normal and reasonable comment. I think the thing that you said about like making the n grow a little bit faster, and that would complete like the proof of theorem 1, which is the result related to uniform validity. Something like that occurred to me maybe like a month or 2 ago, and I'm not surprised you got it. And yeah, anyway, yeah, that was cool. Yeah, like I really appreciate you reading the paper so carefully. Anyway, I actually want to talk though today about the empirical application because it's something that I'm thinking about, and I think there's definitely some questions that will probably come up, but it's something that I'm excited about. So I just want to give a little bit more context about the empirical application. Luckily, we had Maria and Matt talk about this setting before, so like I don't have to give all the context. But basically, the context is related to making counterfactual predictions about Medicare Advantage. and specifically about how enrollment in that government program responds to payment policy. And the reason why I'm looking at this is, like, suppose you're a policymaker and you have to make a prediction and you only get to make one prediction, right? This kind of family of methods, model selection, is like kind of nice for picking which model you're gonna use to make a prediction. The reason why specifically this literature is because basically there's a literature that tries to predict how enrollment in Medicare Advantage will respond to payment, but it's kind of a little bit all over the place in terms of what it's predicting. There's some studies that are looking at identifying variation from like the Benefits Improvement Protection Act that get like pretty medium-sized numbers, like, you know, maybe $100 benchmark or a 10% benchmark increase will increase enrollment by like 30%. And there's other papers that are like using exogenous variation from like after the ACA that are saying that like the same policy would have like, you know, like a 1 or 2% impact on enrollment. So like, you know, if you're in a setting where it's like gotta pick one or the other, like, you know, you could maybe take the average of the two, or you could be like, maybe there's a selection that we should be making. And that's the motivation for this empirical application. And it's, you know, something that I've only started working on in the past year or so. So like questions are gonna be welcome, and want to not talk too long so I can take questions about that issue. So just something that's come up a bit that I just wanted to quickly touch on. And I think Xiaoxia actually asked about this directly, is, you know, you have these different models like estimating how enrollment in Medicare Advantage will respond to different like exogenous, you know, policy shocks that change enrollment. Why is log likelihood the criteria that you want to be using? So in general, like if you're trying to like use a model selection test to select between different models for counterfactuals, log likelihood may not be the criteria that you necessarily want. Log likelihood is going to prioritize a few things, but it's going to prioritize, one, the size of the affected like treatment group, like more people treated, like higher log likelihood, and the other is going to prioritize like exogeneity of the intervention. If the intervention like is truly exogenous, then your model will be close to the true data generating process, and log likelihood will make your model look good. So you know, like when you're just generally trying to make predictions about like a 10% benchmark decrease across the board, like log likelihood, you know, at least I think should be fine. Of course, you know, if you were trying to make predictions about something more like, you know, specific, like, you know, maybe Medicare Advantage enrollment among like dual eligible beneficiaries, like maybe log likelihood isn't the criteria you want to be using to select a model. So now I just want to quickly talk about the results of the empirical application and kind of highlight what they are, and just to talk through that. Basically, so one thing that Xiaoxia mentioned was like a lot of tests are rejecting the null. Actually, this is one where I wasn't able to reject the null. Basically, I had my two interventions. One of them was related to both sources of variation after the ACA, but I was looking at like an event study model using double bonus payments to Medicare Advantage plans, and another event study model using like benchmark cuts to Medicare Advantage plans. And these are two policies that differ based on geography, and they differ based on like, do the cuts increase or decrease payments. And surprisingly, like I wasn't able to reject the null that these models are like, you know, are getting like that these models are equally close to that the one model is farther from the truth than the other. So you know, that is basically ruling out one of these two differences as a reason to, you know, argue that one model is better for counterfactuals than the other. One thing that the two sources of variation have in common is that they occurred in the same time period, which, you know, maybe points to reasons why you might want to prefer one's, you know, answer in the literature over another. Lastly, I want to talk about the like interpreting the results and like interpreting the coefficients. So like this method is easy when you think about it in terms of counterfactuals, because what you're selecting is a model to do counterfactuals with. So like basically, like I'm thinking about what happens if you know, change benchmarks by $100, and you know, one model is predicting enrollment will change by like 0.15%, the other model is predicting enrollment will change by 0.2%. So pretty close, which maybe isn't surprising, but I will say like this, you have to, when you're using this kind of method, you have to be thinking about like selecting between counterfactuals like I have two different sets of predictions as opposed to like doing like a treatment evaluation approach. So, actually doing inference on the parameters after you've made a selection between the two models is tricky. And Xiaoxia's written about that problem, and it's a cool one. So with that, I'm gonna open to questions. Yeah.
Okay, so thank you very much. So I have two questions, both of which are perhaps naive. So first of all, obviously your framework pre-specifies a fully parameterized likelihood,
Yeah.
which is typically not the case in the GMM. Well, it's not the case in the GMM-like models, right? So I wonder if we could just replace them by something like empirical likelihoods, and still your results will go through. So that's the first question.
Yeah.
And generally, well, what do you do in the GMM type frameworks, right? With the Wong test. And how do you specify the likelihood? Yeah, and the second question, okay, please answer. And
The answer is I'm thinking about fully specified likelihoods on GMM. That's an extension that I thought about though. Yeah, and I'm doing like parametric standard errors or parametric errors for the two regression models.
all right, so far there are no results
Yeah.
of Wong test with a semi-parametric framework.
Yeah.
Okay, good. And then, so how do you specify the likelihood here for your empirical application?
Like just fixed effects, like normal standard errors, kind of like it's these are standard event studies that you would kind of expect, like.
Yeah. And I guess I have another comment, and Xiaoxia touched upon it, the fact that under certain scenarios in which your truth is close to the models that you specify, or even lies within the models you specify, the distribution of the test statistic is degenerate, right? It goes down to zero, right? If bootstrap works in these scenarios, this will go against common wisdom, right? That bootstrap is only valid when
Yes.
the statistics are asymptotically normal.
So I mean,
So
basically,
that would be hard to explain
Yeah.
why it is. Yeah.
that's not what I was. I mean, like I think that, as Xiaoxia pointed out, I think part of the benefit of if you're trying to I imagine most people in this room aren't trying to do model selection, and I have an opinion about that. I think that in situations where you're between two different counterfactuals, you could just average the two models. But another option is if you don't, maybe you don't want to do that because you think that one model actually is better than the other. There's a variety of reasons why you might want to do that, and talk to me after if you're curious. This is what you're gonna do, but then this is a good method, and then there's this issue of uniformity, and there's a lot of solutions, but bootstrapping is a very clean solution. It doesn't really deal with what you're asking about with this the situation where both models are kind of very this close to overlapping case. Basically the test statistic is degenerate in that case.
Right, and then a final super quick question is, what do you do with post-selection inference? Because I can imagine your standard errors after you select the model are biased downwards.
Yeah.
Or it depends on the model, or can you?
No, so I'm just reporting regular standard errors, but I'm not trying to solve that problem in this paper.
Okay, but probably there is such a problem, right?
Yeah, Chef has written about it.
Yeah. Thank you.
Can I say a bit more for Eric about the bootstrap validity? So it's true that the conventional, if you just do a naive bootstrap without any adjustments, then it doesn't work in this case. We know that, but that's not what Eric proposes. He proposes to do adjustments. The most important thing is the adjustment in the denominator, the tuning parameter Bn. That's gonna make sure that the bootstrap will provide a valid bound in the degenerate case. So that's how you can make the bootstrap work sometimes, but not the naive bootstrap without any adjustment.
Yeah, sure. So you've raised the issue of model averaging a couple of times and then sort of brushed it off.
Yeah.
I don't want to do that, right? So it seems to me over here, if you think one model is better than the other, yes?
Yeah.
Some kind of model selection criterion tells you one's better than the other, then maybe you want to lean towards the better model. Maybe you want to put all your weight on that model average in towards the better model. But in all of the pictures, in some sense, the truth is sort of equidistant to the two models. Maybe it's really far away, maybe it's really close. Let's suppose that they're really close, or in fact, both of them nest the truth. Then why isn't for the practical policy issue that you're talking about, right, which is sort of driving my thinking, that at the end, the policymaker wants one answer. You don't want to say, well, it could be this or it could be that. They want one answer. Then why is the model average not the better answer? And I'm not talking about a naive average, I'm talking about something, right? I mean, maybe we go Bayesian here and figure out what the correct average is.
Yeah, so I mean, this is something that I'm actively thinking about. I have like intuition that like, you know, averaging something wrong with something right, you maybe should just try to figure out how to pick the right thing. Like kind of that's like kind of the short answer. The longer the reason why it's not as simple as like averaging something wrong with something right gives you something that's like slightly wrong and slightly right. Like the reason why it's more complicated is then like, okay, like why is log likelihood helping you to figure out what's right? And the short answer is like it probably isn't, and that's something that I'm kind of working a lot on is like what's the criteria that will help you pick the right one and tell you know figure out which one's wrong. But the short answer is, you know, if you average something wrong with something right, you just get something in the middle, which yeah, I don't want to do that. Yeah.
So one idea I had talking about thinking about model averaging is that I wonder if you could use your method to select best model at the subgroup level, which would lead to a super learner kind of approach in the sense that you're picking the best model for certain segment of your prediction space, right? So so it's not the same model every time, which is kind of the basic idea of a super learner, right, in machine learning. And so if you could do model selection at that level, not for the whole data, but for certain subgroups and then average, would you have a better prediction? It's kind of model averaging, but I think you can use your technique to actually come up with the selection criteria in a better way, I wonder.
I mean, you're saying that like, oh, like, you know, do the tests at each county to pick a model.
Yeah,
and
exactly.
That's
exactly,
how
exactly. And then get the overall.
Yeah, I mean, that sounds super straightforward. Yeah, maybe, you know, you want to have different counties with different models. But, you know, like this is looking at this, like I think what you described sounds straightforward, but how to do it in just one county, that's the tricky part.
Right, and but I'm saying that the likelihood function could easily extend that you don't need to rely on the same model for every county, right? And you can apply that at that level. I mean, at the limit, you are applying it at the individual prediction, the likelihood of the individual prediction or something like that, right? So which is kind of at the limit, it goes to a super learner kind of approach.
Yeah, you're saying, yeah, maybe I misunderstood. You're saying that like actually make you're saying turn this into a classification problem.
Yep.
Yeah.
Yeah.
I haven't thought about that, but I think there's probably connections, yeah.
Any last questions from folks? All right, I think. Now you can hear me better. All right, I think we have a break now, so give a round of applause for. We'll be back here at 3:30.